OK, so let me show you an example of a voltage clamp. OK, this is now will be a step of voltage. Remember, we looked before at a step of current injected to a cell. But in this case, we are talking about voltage clamp of the Hodgkin-Huxley technique. Actually, it was developed by other people, the voltage clamp, but Hodgkin used it with Huxley for the squid giant axon. So here is a voltage clamp. You start from rest, you clamp the membrane, you jump. And you decide that now the difference between the inside and the outside is not minus 60, but it's, let's say, minus 50 here. This is fixed. You cannot change it anymore. So the difference between the inside and the outside is now minus 50 rather than minus 60. And you record the current that you need to inject in order to fix this voltage. And you see the capacitive current, because when you jump the voltage, as we know from RC circuits, there is a capacitive current. Just because there is a change from this voltage to this voltage, dV, dt, there is a dV, there is a voltage change from here to here. So there is a capacitive current. And then you fix the voltage, so there is no capacitive current anymore, because capacitive current is sensitive to the change in voltage. But there is no change in voltage anymore. Here it's fixed. But you get current through the resistance, the resistive current, as we knew before from an RC circuit. So this behaves basically like a passive RC circuit, passive. There is a capacitance, and there is a resistive current. This is already what we know. Nothing special here. This is a subthreshold regime. It's the subthreshold regime. What happens when we depolarize the cell further to the suprathreshold regime? Something very interesting happens. So here I start from minus 60, but in this case, the voltage clamp jumps from minus 60 to 0. So this is a depolarization of 60 millivolts. And then I fix the voltage clamp. So now there is a voltage clamp to plus 60 millivolts relative to rest. Look what happens to the membrane current. I'm now showing you the membrane current. This was a surprise. This was amazing. This is really a revelation, because suddenly you see something new. First, you see the capacitive current, as before. Just because you change the voltage from here to here, there is a capacitive current, dV dt. It's a big dV dt, so your big IC, capacitive current. But then, when you hold the voltage, at plus 60 millivolts relative to rest, you see a strange phenomena. You see that very early on, there is an inward current from the outside into the axon. This is an inward current that is activated, inward current. You continue to hold the voltage. This inward current becomes smaller and smaller and smaller and smaller and smaller. Then it reverses and becomes an outward current from the inside of the axon outward. So you see that during this suprathreshold voltage clamp, you get first an early inward current, activated inward current, and then it reverses, it inactivates, and it becomes an outward current. So it's a biphasic current. Although you hold the voltage fixed, and there is no voltage change between the two sides of the membrane, it's the same voltage. You get an inward current and an outward current. This was a new phenomena. Nobody knew that the underlying currents in the squid giant membrane during a voltage change, a voltage clamp, consists of two basic phases. The inward fast inward activation of the current and then inactivation or reversing of the current and then becoming an outward current. This was new. What they also found that you can block these two currents separately. They found that if you use a very potent drug, a very dangerous drug that you can find in certain fishes, the tetrodotoxin, the TTX, if you put on top of the axon in the dish, if you put a very, very low concentration of this TTX, you can get rid of one of those currents. So this is what I showed you before. During voltage clamp inward and outward current, when I place TTX on the axon, on the squid axon, the first phase, this phase, the inward phase disappears, and you are left only with the outward phase of the current. So here, during voltage clamp, you see only outward current. This is in the presence of TTX. So the early fast inactivating current, activating, inactivating current disappear, and you are left with only one type of current. So using pharmacology agents or drugs, using drugs, you start to separate two currents. The early current seems to be different than the late current, because you can stay with the late current and get rid of the early current. They also found another drug, the tetraethyl ammonium, or the TEA. This drug, when you place on top of the axon and you do a voltage clamp, you find something opposite. So here is the voltage clamp, like here, and suddenly you see that the late phase, the outward phase, disappears. And you are left only with the inward phase. So they came to the conclusion, Hodgkin-Huxley, using this separation technique using drugs, that this response to voltage clamp, this current response, this membrane current, the inward and the outward, are probably two different currents. They are not the same current. They behave differently. They can be blocked separately. One with TTX, another one with TEA. And they found, using other techniques, changing the concentration of sodium and of potassium. So they played with the concentration, both inside the axon, because it's so big, they can change the internal concentration. They can change the external concentration of both sodium and of potassium ions. They found very, very clearly that the inward current is a sodium current that flows from the outside to the inside. So this is an inward current. The Na, the sodium current, flows from outside inside early on during the voltage clamp. So very early on, just after you voltage clamp, some ion channels for sodium are apparently open, and this sodium can flow from outside into the cell. This is this part. Interestingly, you can see that this sodium flow is activated, so there are some opening of channels, opening of pores that enables the sodium to flow inside. But if you continue the voltage clamp, you see that this inward sodium ends, inactivates. So this current has two phases apparently, the activation phase and the inactivation phase of the inward, fast inward current. We call it fast inactivating sodium current. This is the first one. And later on with time, there is a second phase, which is an outward phase. This is the blue current here. And they show that this consists of potassium ions. So potassium, at this time, the potassium flows from inside outside. This is the outward current. So the spike, basically, we shall see, because this is just one voltage and the spike goes all over the voltages because it is going up and down. But for this voltage, you can see inward sodium current, fast and inactivating, and later potassium current that appears later and seems not to be inactivated. You can see that you can continue the voltage clamp and the outward current does not inactivate. This is an inactivating current, activating, inactivating, and this outward current is not inactivated. It's activated and remains open as long as there is voltage clamp. So what is the circuit summary of what I just said? This is the drawing by Hodgkin-Huxley from 1952, the fourth important paper from this year. They summarize what I just showed you with an electrical circuit of the axonal membrane. We already saw circuits for the passive membrane. We saw circuits for the synaptic membrane in the dendrite. Now I show you a circuit for the axonal membrane. And here is the circuit. There is a capacitance, Cm, that you already know. There is a leak or passive channels. As always, there are all these channels that we mentioned that are passive, static. They don't depend on anything. This is what we call the R or R leak, the passive channels. So this is what we saw before, the C and the R. But here the Hodgkin-Huxley added two conductances. The sodium conductance with a positive battery inside. So whenever this conductance, which is voltage dependent, and we call it excitable because it is a voltage dependent, and when I clamp the membrane suprathreshold, I get current flow, sodium current flow from outside to the inside through this opening of this resistance or this conductance, the sodium conductance with the associative battery. And there is another conductance, the potassium conductance. So this is the potassium conductance with a negative battery looking inside. So whenever you open this conductance, potassium actually flows from the inside outside. Not like it is here, but eventually it goes from here outside. So this is the inward current, this is the outward current, this is the leak current, this is the capacitative current, and basically this equation comes, this circuit ends by saying that the total current in the membrane is the capacitative current plus the voltage dependent excitable sodium current, the voltage dependent later potassium conductance, and the passive R leak conductance. This is a very unique circuit because it exists mostly in axons. This voltage dependence, this is what is unique about axons. They have a strong special channels, special ion channels that depends on voltage. And whenever there is enough depolarization, these channels come into play. They are opened. This channel opens fast, but it inactivates fast also. So it opens early on, and then it closes, inactivates. And this potassium channel opens a little bit later, and when it opens, there is a current flow from the inside to the outside. This is the classical conceptual jump of Hodgkin-Huxley in their voyage, in their journey to understand the action potential, drawing this circuit. But this is not enough. They need to do more.